So we're going to be making some calculations for the center of mass here, and we've got our formulas here set up. Some of this stuff is pretty familiar for us. We've got the calculations for our individual coordinates, which we recognize as taking the moment and dividing it by the total mass. We also have our total mass over here, which of course is just the integral of the density. And then probably new to us is our equations that we're using for calculating these moments about the yz, the xz, and the xy. And the way that I generally remember these things is when you want to compute the moment about yz, it's going to be x times the density. The moment about xz is going to be y times the density. And the moment about xy is going to be z times the density. So you'll notice that the one missing variable over here on the left side in the moment statement is the one that appears times the density in the integrand. So that's my little device for memorizing those formulas. Other than that, they're pretty straightforward. And then, of course, we've got the calculations for our individual coordinates as well. So you'll notice similarly, you've got moment about yz is going to be x bar. Here the y is missing, that's y bar. Here the xy, z is missing, so that's the z bar. So again, just kind of my device for memorizing what those formulas are. Beyond that, it's really just a matter of setting up the integral itself. The actual integration won't be terribly challenging for us, mostly because of the fact that we've got formulas that we're using for our density functions that are not terribly complex. So again, most of the emphasis here is really put on setting up the triple integral, interpreting the region that we're given, and then of course we can make the calculation from there. So let's take a look at an example of this. Suppose we have a region E, and it's going to be a solid bounded below by the cone, z equals the square root of x squared plus y squared, and above by the paraboloid, z equals 2 minus x squared minus y squared. And we're going to have a density function here that's equal to x plus z. So let's start setting this up. Again, really it's about determining what the region looks like. The good news is once you understand that region and have those limits, every single one of these calculations is going to have the same limits. You're integrating each of these over the exact same region. So the limits get applied to every one of these four integrals, and then we have our integration from there. And in this case, we're going to end up using cylindrical coordinates, so we'll have to make sure we convert everything over as we're doing that. So here's our coordinate axes, and as I typically like to do, let's sketch a cross-section of what this looks like. Here's the xy plane, and of course this is the z-axis then. So we're bounded below by the cone, so we'll have some kind of cone coming up from either side like this, and above by a paraboloid, which will look something like this maybe. And we can now see what this region is that we're working with. We're inside this sort of ice cream cone shaped thing. We can kind of try and make that look a little three-dimensional here if we want to add some detail, just so we can kind of visualize again what's happening. But, you know, probably an ice cream cone is about our best analogy at this point. So that's the region. So we're going to need to figure out then what the region in the xy plane is, which is going to be the projection of this circle of intersection, and that's what we'll be integrating over in the xy plane over the region D. We can also grab from this that our lower surface is going to be the cone, and the upper surface is going to be the paraboloid. So that'll help us set up those z-bounds. So now I can grab that z is going to go between the square root of x squared plus y squared on the bottom, and on the top, that paraboloid, 2 minus x squared minus y squared. So this will need to get converted to cylindrical coordinates. I think that might be the best choice for us here. We might be able to do it in spherical, but cylindrical seems like a natural fit. We've got our circular region down here in the xy plane, and we've got some nice simplification here for our bounds here, because x squared plus y squared is equal to r squared. So this is going to turn into r less than or equal to z less than or equal to 2 minus r squared. And just factoring out a negative 1 here gives us minus x squared plus y squared. So that's where our minus r squared is coming from. So there you've got some bounds for z. Now we need the bounds for r and theta. Again, that's going to come from this circle of intersection here between the cone and the paraboloid. So let's go after those. So we'll need to set the two equations equal to each other in cylindrical form. That says that r is equal to 2 minus r squared, or r squared plus r minus 2 equals 0. And that will factor into r plus 2 and r minus 1. So we get two values. Obviously, this is going to give r equals negative 2, and this is going to be r equals 1. This one can't happen. We can't have negative radii for our problem, so that means that r is equal to 1, which we probably could have determined another way, but this is pretty efficient. So that's the range of values then for r, basically. It's going to go from 0 to 1. And then we need theta. In this case, we're going all the way around, so 0 less than or equal to theta less than or equal to 2 pi. And there's our limits. Okay, so I've kind of reset here so we can complete out our integrals. We've got our limits of integration as well as our density over here on the right. And it's really just a matter of filling these things in at this point, making sure that we're careful as we do it. So we'll take the mass here, which is going to be our triple integral of the density function, so just r cosine theta plus z times dv, but of course for cylindrical coordinates, dv is r times dz dr d theta. And let's be careful and get some parentheses around that so we don't miss our distribution. Of course, now the limits, z is going to go from r to 2 minus r squared. R is going to go from 0 to 1, and theta is going from 0 to 2 pi. And they're all going to play out pretty much the same. So let's go ahead and get the moment about yz. Again, we're going to have our triple integral. It's going to be x, which in cylindrical coordinates is r cosine theta, times the density function, r cosine theta, plus z, r dz dr d theta. And the limits are the same for all of our integrals, so we'll just carry those down. Setting up the integral from the moment about xz is y times the density. Y is r sine theta times our r cosine theta plus z times r dz dr d theta. Of course, z goes from 0 to 2 minus r squared. R is going from 0 to 1. Theta 0 to 2 pi. And finally, the moment about xy. Get our triple integral. This is z, which in cylindrical coordinates stays the same. R cosine theta plus z times r dz dr d theta. Throw on the last limits here, and we're done. So those are all set up now. It's just down to making the actual calculations for those antiderivatives themselves.